Hello, people. How y'all doing? This is lecture, I believe, number 4, and we're gonna head right into it. It's gonna be a short lecture because it's actually pretty easy. This section just tells you, we've been doing a function in terms of x, but now we want functions in terms of two variables, x and y. This is you just plug it in, so nothing interesting here. This is you plug it in as well. Take 160 and 68. That's like your x and y, and you plug it in and you get your answer. Okay, so function of two variables is a rule that assigns to each order pair of real numbers. In a set D, unique real number denoted by this. Set D is the domain of f, and its range is the set that f takes on. So when you have this, would be your range, and your D would be your domain. All right, D for domain, duh. How do you find the domain and range for a function with two variables? You find it the same way you would find it for a function with one variable. So you split it apart. Sine, here that you have no restrictions on the domain, right? On the domain, there's no restrictions, but on the on the range, there is, because sine, as you guys know, is between 0 and 1, negative 0 and 1. So you can read the domain like that, but because it has other variables beside it, that is not the only range, so you can't really write it as the range. Make sense? So my e, what is my e? Here I cannot square root. Here, my root cannot be less than, right? My root cannot be less than 0. Because if it is less than 0, this becomes negative and you can't square root a negative. So x plus y. When we say what cannot be a 0, it means x and y has to be more than or equal to 0. You can root 0, but you can't root a negative number. So that's our domain here. This part, your denominator can be 0, right? So you would say x3 minus 8y, and now be 0. Oops, forgot my 0. All right, and these are your two restrictions. You have your x plus y squared has to be more than 0, and your x3 minus 8y and not equal 0. All right, and so that's one. Now you can technically isolate, like you could take y to the other side and you can be, you could do this, where now your range for x has to be more than the whatever value of y but squared. So that's one way. Okay, so going to the next part. Finding the domain of a function and illustrate it graphically. All right, so like we said, this cannot be negative because square root. So y minus x has to be more than or equal to 0. You cannot ln a 0 number or a negative number. So 2x plus y has to be more than or equal, no, sorry, not equal, but has to be more than 0. Because you cannot ln 0. And you see your last variables here, no restrictions, and here, no restrictions. And so now we got our two domains. And remember how earlier I said you could take this to the side? So we can say y is more than or equal to x. And I can say y is more than negative 2x. And now I got my two domains. And you see, since this is y more than or equal to x, it's like saying y equals x. And so you got a linear line. Since this is negative 2, your line is a little bit less steep, or more steep, I'd say. And it's the negative, so it's the opposite direction. That's how you get this. All right? I'm trying to run through this really fast because we're running tight on time. The midterm's tomorrow. Some people are doing it today. If f is a function of two variables with domain D, then the graph of f is the set of all points x, y, z. Such that z equals y equals f, x, y, and xy is D. That was a lot. Hard to explain. Not hard to explain. Hard to understand from the reading, but to explain it, if you want to find, so if I gave you y equals mx plus b, you would set y to 0 and find your other stuff. And then eventually you set your x to 0 and find your y. Here, you could do the same thing to find the intercepts. So if I want to find the intercept at the x, I'll set everything else to 0. Because when you look at the graph, right, this is my x, this is my y, this is my z. When x is 0, where it intercepts x, where, like, if I intercept x here, or if I intercept x here, I'll zoom in, then my z will be 0 and my y will be 0. Now if I intercept the y here, you see my x is 0 and my z is 0. If I intercept the z here, my y is 0 and my x is 0. And so if we want to find the intercept of x, I'll just set everything else to 0. So 2x plus 0 plus 3, 0 equals 12. And then we'll get, 2x equals 12 and x equals 6. So this intercepts at the 6 mark. And our y, same thing. You get 2, 0 plus y plus 3, 0 equals 12. And we have an intercept at 12. And for my z, I have, what do we have? 2, 0 plus 0 plus 3 z equals 12. And then z equals 4. And now when we graph this, same thing, so make a straight line. All right. You guys see, I learned this new technology. Look at this. Makes a straight line if I just keep holding it. So we know there's an x-intercept at 6 when everything else is 0. So x, let's say this is x, y, z, and so we have a point at 6. And we have a 12. And we have a 4. There you go. And you know how when you sketch, usually on your x and y, and you get 2 points, you connect them. So you'll do the same thing. You just gotta connect your third one, right? And so that's basically what it looks like. That's how you can sketch stuff. There is another one. There's this one. So if we do the same thing, let's say you come here and you want to do the same thing. You're like, I don't know what to do. Whatever. You'll get your x. Let's say we're solving for x, so you get x squared equals, because everything sets to 0. 49 root of 49 is 7, I believe. Let me confirm. Root 49, 7 equals 7. And that will obviously happen to all of them because they're all the same. So my y will equal 7 and my z will equal 7, right? And so if we were to come here and we were to graph it, I'm sure there's a way to do like an arrow too. Like, no. I guess not. Okay. So if we were to graph this, what we get is on the x we have 7, on the y we have 7, and on the z we have 7. All right. Now this will actually look like a ball. Ooh, because of that square, like a 3D ball. It is a little bit hard to visualize, I would say. I would say you could remember your, r equals x squared plus y squared. Right? Now you just have r squared equals x squared plus y squared plus z squared. Because this will give you a circle in 2D. This gives you a circle in 3D. Right? Okay, so the level curves of a function f of 2 variables are the curves with the equation f of x equals k, where k is a constant. In the range of f, that's the y, or range. A graph showing level curves is called a contour map. So what happens is, how can I explain this? Because I feel like if we go through examples, you guys will understand it better. Okay, so I think that's what we're gonna do. We're gonna pass through this one and we're gonna explain it here. So how do you match these? Right, I'll show you guys a couple ways you can match these. The color, you see how this is bright red and there's yellows. The color is one way. Second way is the shape, obviously. And so what does this mean? When you have your, so you see this graph on this section and these sections look pretty. Whee. These sections right here, you see how these are coming up? When they come up, they turn yellow. And when they go down, they turn bright red. So up equals yellow, down equals red. Okay, and this is not necessarily the case. Just because it depends how they're using their what do you call it? Like their coloring, so the colors might change. But we can go off based off this one for in this case. The other way you can find it is the shape that's coming out is circulated. So imagine you're processing this, then you're processing this, then you're processing this. You see how it becomes like that as I'm going down? What something that's like circles like that? This one, there's one in the middle. So if I were to draw this one, if I were to like think of a way to draw this one, I would say, so I would have my square, right? And I would say I probably have like maybe something coming out like this. That's one way. That also actually applies to like this one somewhat. Okay, but you see this one, you see these are four, what do you call them? I don't know what's the terminology for this, but you see how there's four of these coming out, and I said how you're processing circles. Look at this. That's the same thing. This one has a lot. Okay, so this one actually represents a lot like B. You see how you have these circles coming out. You see how you process it, and you see like in the corner, this is bright red, and then the yellow is up. So you see if you look at your top left, that's up. That's the up. That's the yellow part here. Okay, so this is your B, and this is your A. Now we also had earlier that we represented this as this, right? Or this one. And you see this one also has a similar characteristic. But what is the difference? That is a question. The difference is on the middle, you see right here is a circle. And this circle fades out like this inside, right? Because you're going inside. Right? So that fades out like it's like a slide. And then on the outside, there's also a slide, and then there's spikes on four spikes on the edges. And so what's something that has four spikes on the edges? That's what I want to see. Is there something that presents four spikes on the edges? No, there isn't. Okay? What else is there? There's a space in the middle between this and this. Is there something with space like that? That's not evenly, so it's just it looks fine in the middle, and then there's a drop. You see, like this one looks fine in the middle, and then there's this weird empty space. There's another weird empty space. Two weird empty space. What could these represent? Huh. Maybe these represent this hike up and this hike down. Right? This edge right here and this edge right here. So these could be these two things. Right? Maybe they're not showing those spikes. So we can, I don't know why I put this as A. This is supposed to be D. Alright. We can say this is A then. Right? Now the question is, what represents this? You see how this is smooth? The spacing beside it goes out smooth. That means it's a smooth movement. And since it's circle, that means it's either pressed down or it's pressed up. That's what circles mean. Either pressed down or pressed up. What's something that's either pressed down or pressed up is this. This pressed straight down, it's smooth, right? And so this must be your F. All right, now 2. If you can see 2, you have these little circles here. All right. Now, what could these circles mean? It could mean there is, let's say I have like a page, right? and right here I have like dense. But the thing is, there's these waves as well. Let's see what these waves match. Does any of these have waves similar to like these? And as you can see, you could go like here. But this is the side view of it, so it's not visible. These demonstrate the top view, so you wouldn't be able to see these. This one is one way, right? These ones are actually very similar. And as you can see, in the middle, there's these little dents. And so that represents it pretty well, don't you think? So that could be your C. Okay. Now, how do you understand this? So as you can see, you see how this color is like a little bit yellow. This is more reddish. That means one side is going down, one side is going up. Okay. So this one, obviously. But assuming you don't see that either, what other ways can you demonstrate this? You see this edge goes down while this edge goes up. You see, if we look here, this edge, you see we said down is red. Well, actually, but you see, like, that doesn't follow in this case. But the coloring match, so even if you have different colorings, you would be able to what do you call it? Decipher this. Because the other thing is, you don't really know if this is like which direction you're looking at this graph from. So, but you can match them like this. Like the coloring does matter. And you see the yellow and the red, that means these are like opposite directions. And as you can see, opposite directions is the same with this edge and this edge. And you can see the same thing here. This is yellow and this is red, right? And in the middle, you see there's nothing because it's flat. This middle is flat. This represents the indentation, whether you're denting up or you're denting up. Oh, sorry, whether you're denting up or you're denting down. And so, since in the middle there's no indentation, there's nothing, nothing here. And you see, this is very similar with if you look at other things, like for example, this one. In the middle, right here, right over down there, there's no indentation, because it would be flat with the floor, right? And so that's why there wouldn't be any indentation there. Another thing you can check is you see here for this one's D. If we go to D, you see right here, this is with the floor. And you see same thing. Okay, so that's how you could understand these. All right. Now talking about weather, representing different things. Find the domain of f, x, y, z on this and this and this exercise. Well, the denominator, z can be 0, so z cannot be 1, because if you put this as 1, minus 1, it's 0. Sine has no restrictions. Ln your x plus y squared has to be more than 0, because you cannot ln 0. And so what you'll get is this. Pretty easy. This is partial derivatives. They're teaching you first principle of partial derivatives. You don't need to know this. All right. So don't worry too much about this. We'll go into the quicker derivatives. And so if z equals f of x, then this and this and this. What the hell does this mean? All right. So if I want to find, so remember how I have now, I have a function. I don't know why I wrote that like an integral. I have a function in terms of x and y. And this function is like sine x plus y squared, let's say. How do I differentiate this? You can't have dy, dx, and differentiate in both terms. You can't do that. So what you can do is you can differentiate in terms of x. So when I differentiate with this little x subscript, when I differentiate in terms of x, what I'll get is I will treat my y as a constant. Let's say I, derive this, I'll get cos x, right? I derived my x, plus this is my y squared is a constant. So when you derive a constant, as if you're deriving 10, this goes to 0. So that's what it looks like. And same thing for y, you would regard x as constant and differentiate in terms of y. Right? So if we take this and we differentiate in terms of x and y, so my x will equal e to the x 3 plus y2. This stays the same for Euler. And you multiply by the derivative of the exponent. So since we're deriving in terms of x, I'll derive my x, which is which is 3x to the power 2, plus y, this is a constant, so this goes to 0, so plus 0, plus this in terms of x would be 5y, the constant stays, so if y was a 10, you'll have 510, and then now you derive your x, which is 2x, and then plus y, this goes to 0, okay? So when you simplify this, you'll get e, I'll zoom in, you'll get e to the x3 plus y squared times 3x squared plus 10yx, right? And now for doing the y, you'll do the same thing. So, right, and then times the derivative of the top. Your x goes to 0 because we're deriving with respect to y. So you'll get your 2y plus, these are constants, so they stay the same. And then I derive my y, which is just 1, plus derive my y here, which is 3y squared. That is your derivative in terms of y. All right. Now the question here says, in something something, you get some equation where v is the wind and speed per second, whatever. It said find wt. So this is like saying f of x. I don't know what the fuck was that. X and y. Some equation. What they're giving us is w, v, and t. And you know how when we want to derive in terms of x, we treat y as a constant. Right now, what they're telling us is find w in terms of t, so we treat v as a constant. Okay, and they give us some values that we'll plug in later. But now let's derive this in terms of t. So my 91.4 goes to 0 when I derive, that's a constant, so it's 0, minus this whole box is a constant. Okay, 10.45 plus 6.69 root v, which we said we're going to treat as a constant, minus 0.447 v. This whole thing is a constant, divided by 22. This whole thing is a constant. If I take this and I set this as a variable c, okay, so let's say I set this to variable c, and then I continue times 91.4 minus t. Now I gotta derive this, right? And so let me derive this. So let's say we expand c 91.4 minus ct. This is constants. When you derive a constant, it goes to 0 because we're deriving in terms of t. And so what this will equal is a negative ct, right? I forgot to include this negative in my thing, so let me include it. So I'll include this negative in my thing. All right. And so this is my answer. Now let me sub c back in. So my c equals, so I'm going to keep this negative. This negative comes here. Now I have this other negative here. Don't forget that. So when I do this, I will get 10.45 plus 6.69 root v minus 0.447v, right? All over 22. That's my c. Now, so this is not done yet because I haven't derived, right? So when I derive this, what I get is negative c. Because my t is 1, minus 1 is 0. So my t goes to 1. Goes to 1 when I derive. And so, yeah, I just get negative c. And so, that's my answer. Now multiply these cancels out. This would be your answer. And now they're telling you sub these numbers in and find your value. So if I've done everything correctly, I can just sub these in. Oh, whoa, where's my man? Okay, there it is. So if I sub my 20v, I don't have a t, right? So let's sub the thing in. So equals, we have 10.45 plus 6.69 root 20 minus 0.447 20 all over 22. And that's how you do it. And that would be your answer. And so if I plug this into my calculator, I'm just going to do it to confirm my answer with the prof. If I did my work right. I want to teach you guys false information. 10.45 plus 6.69 root 20 minus 0.447 20 all over 22. And I got 1.428. All right. Now, they tell you interpret what this means. I'm not going to interpret what this means because I do mathematics here. And this is interpreting stuff. It's not mathematics. It's too much English for me. So I'm just going to go next. Also, you're not going to be asked to interpret things. So that's why I'm not coming through it to save time. Now, how do you get a function of two variables, x and y, then its second partial derivative? How do you get the second partial derivative? And so if I want to get second partial derivative in terms of x, what I'll do is I will derive in terms of x, you know, my f at x, and treat any other constant, any other variable as constant. So in this case, if we had a function of f in terms of x and y, sine y plus y squared. I messed up. This is supposed to be an x, right? So if I want to get my first derivative, obviously I will derive in terms of x. So I'll get cos x, right? And I'll treat this as a constant, and I'll go to 0. So this is my f at x. Now if I get my second derivative, then I just derive this again, which will give me sine. Derivative of course, yeah, sine x, right? And so that's how you get this. You just derive it twice. And that's the same thing how you get this. You derive it the same way, but in terms of y now. So you make this a constant, and you treat this as a variable. Now, how do I get xy? You have to do it in the order they give you. So, what does order they give you means? If they tell you, give me the derivative of x first, then y, what you'll do is first, get your derivative in terms of x, then derive it in terms of y, the same derivative. Let's do this example down here. Let me derive this in terms of x. You see, find xy. So my x, y, first, I gotta get my x. So my f of x equals 6 plus, this is constant, goes to 0, plus 2 times 9 x y cubed. Following? And what this will equal me, 2 times 9, 18, x y cubed plus 6. Okay, now what they're telling me is, okay, now that you got x, get the y. So now I'll take my this, so after you derived it, not the original you get in y, the one you derived in terms of x. Now I'm going to derive it again, but in terms of y. So fxy is this derived in terms of y. So my 18 stays constant, my x stays constant because I'm deriving in terms of y. Then my 3 comes down, and my y becomes 2, plus this is a constant, goes to 0. So what is my solution? 18 times 3 xy squared. And that is your fxy. And if you were to do it the other way, first you'll get your y, then the derivative you get from y, you'll derive in terms of x. You just flip these around. You don't flip them around, but the steps you flip around. You do y first, then you derive in terms of x. Okay, so what does Clairaut's theorem says? The Clairaut's theorem says is when you get the derivative of this, so you know how we got this, and then you get the derivative of the opposite, which is fyx instead of xy, you equal them to each other. If they look the same, so let's say my f at xy, aka this, was the same thing as my fyx, which I haven't gotten, but if you were to get it, if these two equal, then this will satisfy Clairaut's theorem. Okay, so see, suppose f is defined on this d, so f is defined on your x that contains the point a and b. If the functions of fxy and fyx are both continuous on d, so on your range, your function is continuous. If that's the case, then f at xy equals f at yx. So, if they ever tell you that you have a function that is defined on my d, Okay, to find out my D. And it contains a point A, some point they select, and a point B. Okay? If they tell me this, I have a function defined on my X, and I give you a point A and I give you a point B. If the function are both continuous on D, if they're both continuous on D, no holes, no asymptotes, if they're both continuous on D, then they equal each other at these 2 points. Like between these 2 points. They equal each other. So when you take this section and you get your derivative of x in terms of y and then your y in terms of x, they equal each other. And we did this theorem in other physics lectures. So, sorry, not other physics lectures, other calculus lectures, like older ones. I believe like last semester we had the same exact theorem, but for just regular derivatives. It was like, yeah, like f at a b equals f, like f, like f at x equals ab equals f at ba or some shit. Well, some guys then we could probably review it. But anyway, so can we extend the concept to more variables? You'll do the same thing. So see, if I want to get my f of y, I will treat my, if I want to get my derivative of u, I'll treat my w and v as constant, just like I treated my y as constant. All right. And if I want to get like my f u v, then first I'll get my u, treat w and v as constant. Then I'll get my v and treat my w and u as constants in terms of u, of course, and so on. So you could add as many variables as you want, and that is lecture number 4. Thank you.